Okay, so thank you very much, everybody, for coming back. Our next speaker is Julian Chaidez from the University of Southern California. Julian got his PhD from the University of California at Berkeley under the supervision of Michael Hutchins, and he's a renowned expert in symplectic topology, dynamical systems, and symplectic field theory, and also computational methods, according to the title of this talk. So the stage is yours.
Great. Thank you for having me. I'm really happy to be here. It's a great conference covering a lot of different things. So, yeah, great. Okay, so yeah, so today I'm talking about computational methods in Reeb dynamics. So maybe first I'll just kind of say, the topics of the talk so far, have been quite varied. So we've talked about Reeb dynamics, contact geometry. We've talked about rigorous computer-assisted proof, so rigorous computer-assisted math. We've talked about experimental math. We even did some experimental math with the fluids vote. And then we've also kind of talked about connections to topology. So things like knottedness of orbits. Okay, so this talk basically touches on all of these. So it touches on all of this. Okay, and this is good. I kind of picked this as sort of like something that would be relevant to some of the people, and I think it's actually relevant to even more of the people than I thought. So the basic goal of my talk is to explain some methods that I kind of came up with Michael Hutchins to basically kind of probe Reeb dynamics in a computational way. So the picture I want you to have in mind is you kind of have a polytope, and then you have a vector field on that polytope, and in some sense that vector field is Reeb. And you want to understand the dynamics of that vector field in some sense, right? And the second thing maybe I should say about this is that these kinds of dynamics can really help you understand the smooth case, and that's sort of some kind of non-trivial input from the symplectic geometry theory. And yeah, so the kind of goal is to do experiments with Reeb dynamics. To both kind of probe important conjectures, but also to kind of come up with new conjectures about how Reeb flows work. Okay, so the first thing I want to do is kind of talk about some background just to set the stage for what is interesting about this stuff. So the first thing I want to do is talk about convex Hamiltonian systems. Okay, so the setting is a really simple one from the perspective of Hamiltonian mechanics. So the thing I want to consider is just standard phase space. So standard phase space. So this is just R2n. Okay, pretty friendly. So just with the standard symplectic form. So standard symplectic form, maybe I'll denote it by omega. Okay. All right, so this is just the setting of Hamiltonian mechanics, right? This is like where you do like the most classical possible form of Hamiltonian dynamics. Okay, and in particular, a smooth function, so smooth energy function, a Hamiltonian. This is H from R2n to R determines a Hamiltonian vector field. So Hamiltonian vector fields. Okay, so I'll denote that by XH. I'm not going to use that notation that much, but that's how I'll write it here. Okay, and what is the equation it satisfies? Well, it satisfies this equation DH is equal to the interior product of XH with omega. Hey, this is sort of the like, well, okay, so there's a little bit of a sign thing here, which is a matter of convention, but this is basically the way to write in kind of a manifold theory way the Hamilton's equations, right? So if Y inside of R2n is some level set, so it's a level set of H, so a regular level set, meaning one that's kind of where DH is not zero. Okay, so that means it's just H inverse of some energy E. Okay, we're some number. Okay, so in this case, then actually the flow lines, the flow lines of H, these are tangent to the level set, right? That's just conservation of energy. And then also, they actually only depend. So the flow lines actually only depend on one. Right? That's because the Hamiltonian vector field just spans. It's just the vector that spans this sort of kernel of the complex form restricted to the hypersurface. Right? So the omega is a 2 form restricted to the hypersurface. I get another 2 form. And then if I take the kernel, it turns out for basic linear algebra reasons, it's one-dimensional, and it's just the thing that's spanned by this. Okay? And so actually, like, I can kind of forget about the Hamiltonian if the dynamics of this vector field, the kind of flow lines of this vector field are the only thing I care about, right? I can just the dynamics are really coming from the geometry of Y and not from the Hamiltonian. Right? Okay, so the dynamics just depend on the geometry of Y and not on H. Okay. Okay, so now there's like two classes of Hamiltonians that I want to kind of focus on today. The first, so a special class of Y, or a special class of hypersurface, called star-shaped. I'll tell you what that means for. So Y is star-shaped if Y is transverse radial vector field like centered at the origins. Picture here is I have some I have the origin that's 0, okay, inside of R2n, and something that starts of like smooth kind of blobby guy, where if I draw all the radial lines coming from, they all hit the word. Yes.
Doesn't really depend on the Hamiltonian, it only depends on the geometry of Y, but the geometry of Y does depend on it.
Yeah, I mean, I just mean I can forget about the specific H. The thing, all I have to remember is the level set. So like if I change the H, if I change H to like another H with the same level set, even if I change the energy at that level set, it would still, the characteristics would still be the same. Like the flow lines would still be, yeah. So that's what I mean by it only depends on Y. I can kind of forget H, and I'm really going to focus from perspective of thinking about Y, right? Okay, so it might seem like kind of a random issue, but actually a prove is that more or less lines. Maybe I'll say it in a kind of informal way, and then maybe I'll clarify. So the dynamics on are to so some Reeb dynamics for the standard context structure. So on S2 minus 1. Okay, so what do I mean by this? Well, I mean that okay, so if I have a star-shaped domain, then that it's pretty easy exercise to check that that means that that Y is diffeomorphic to the sphere. Okay, and in fact, but you can find contact like a specific diffeomorphism, a contact form for which the flow of this flow on the boundary is just given by the Reeb flow of that contact form, right? And conversely, if I like any Reeb flow of of a contact form for this standard context structure, which I won't describe, will correspond to some star-shaped domain. You can find a star-shaped domain with that Reeb flow. Okay, so this is basically saying, like, if I was thinking about star-shaped things, star-shaped Hamiltonians, sort of intrinsically, they're the same thing as just Reeb flows on the sphere for some specific context structure. An intrinsic. This is an intrinsic. This is an intrinsic like contact geometry characterized. Okay. All right. So on the other hand, there's a special class of shaped objects. There's a natural subclass. Those are convex. Okay, so these are so that by that I just mean boundary of some convex body. So why is the boundary of K for some K? Okay, so here's the part where I draw like an egg, okay, or something like an egg. So the egg is K, right? Y is the boundary. Anything kind of egg, convex things are things where a line, any 2 points in the interior of K, the line connecting them is also line segment connecting them is also in K. So a big example would be if K was an ellipsoid. Okay, and in this case, the dynamics are the same as you kind of recover the dynamics of the harmonic oscillator. If I write down like in corresponding to an ellipsoid, then it's the same. It's like the harmonic oscillator, which is like the standard example in like any physics class. Okay, so here's sort of the mystery. So now this kind of gets accepted too. So okay, so I'll call this special properties. Okay, so the mystery here is that we have this nice, like, kind of purely intrinsic characterization of what it means to be star-shaped, right? Star-shaped is like really easy to say what it means. It just means you're a Reeb flow for some standard contact structure. On the other hand, we do not have such a characterization for convex. And on the kind of at first glance, this might not seem so surprising because convexity has nothing to do with symplectic geometry. But the weird thing is actually that the Reeb flows on the boundaries of convex bodies are actually have like a ton of special properties that the star-shaped ones don't. And we kind of have no explanation for this in the sense that like we have no conceptual reason for believing that this should happen. It's just like we can prove a lot of special things about convex systems. Okay, so let me give you some examples. So check some. But let me do what I said just now, which is convexity plays some mysterious dynamical role. Okay, and so to sort of emphasize what these interesting dynamical things are, let me introduce some notation so I can kind of explain to you all of this, what these special properties are. So let me fix notation. Okay, so first notation, I'll denote y. Okay, and this will just be the minimum period of a closed orbit on. Okay, so actually, before I told you, okay, I'm sort of forgetting about the parameterization of the vector fields. In this case, it's actually not so important. There's sort of a canonical Reeb parameterization, assuming that your convex body sort of contains 0. Another way of saying what this period is it's just you take a closed orbit and you like bound it by a disk inside of R4, and then you take the area of that disk with respect to the symplectic form. That's another way of intrinsically getting a period without actually picking a parameterization. Okay, so it doesn't really matter that I forgot about that. What we have the volume. Okay, and this guy either is like the contact volume of Y, or you can just think of it as like the volume of region that Y bound. Okay, and the last one, I'm not really going to go into detail on this one since it's not the focus of my talk. And the Ruel invariant is something like an average. I'll put this just in quotes. This is some kind of average of the flow of the band. Okay, spatially average patient number. Okay. Okay, so let me now tell you all these things that are true for. Let me tell you all this stuff for convex flows and not true in general. A little table here. Okay, so first I have properties, and then I have convex case, and then I have like kind of the start. So first property, going to be the most important one in the talk, is the fact that there's actually some kind of systolic inequality relating the period to the volume. Right? So here I'm just going to write it like this. Okay, and what I mean by this is that some constant, depending on the dimension, multiplied by the root of the volume. Okay, and there's some dimensional analysis you can do to kind of figure out that this is the right exponent here. You can also just work it out specifically. Okay, so this is a theorem that was first proven by Viterbo. So usually I would refer to it as Viterbo's systolic inequality. Okay, and so this was proven for convex things by Viterbo. Okay, and for star-shaped things, and generally for all Reeb flows on a general contact manifold with no other hypothesis. Alamayo. And this is sort of some kind of analog of the sort of systolic inequalities of Riemannian geometry, right? So in Riemannian geometry, you have Gromov has this like whole theory of like systolic inequalities. And I think one of the really interesting questions you can ask is in what way this is related to those. I personally think there is some relationship, although this is sort of a relatively unexplored. But I think that's why we call it a systolic inequalities. It's similar to that in the spirit of those things. That's one special property, not true in general. Okay, so next property is a sort of similar inequality involving the Ruel invariant. Okay, and so here it says that the minimum period multiplied by the Ruel invariant is always bounded by some constant, a different constant, of course, this one, maybe. Okay, so this basically says like average rotation is less than or equal to the volume. Okay, so this one is satisfied for convex things. So this is something I proved with collaborator Oliver Itmar. We used it to distinguish convex things from convexish star-shaped domains. And of course, it's not true in general. I guess we have that, although a little stronger. Okay, so we have these two symbolic inequality. No, it's not helicity. Yeah, it's not nothing. It is a separate quantity than helicity. I will not, but if you want to hear about it, I'm really happy to talk about it. Yeah. Thanks. What's up? So what you're saying is the dimension of this guy. So I mean, you can do a little dimensional analysis, sort of 2n minus 2 scales like 2n minus 2 conformally, which is sort of interesting. Like you're sort of integrating some quantity over space. So you're sort of losing 2 dimensions from the rotation number. So the thing you're integrating is not really a dimensionless quantity. But I am happy to talk about people with this. I just wanted to list this as another. I will absolutely. I will talk about the relevant variant with you all day. So you are after the talk. Okay, so another property is so it's like sort of a surface which has boundary on a Reeb orbit, sort of transverse to every other orbit. This is of course in dimension. It's the only place where that makes sense. Okay. So this is yes. The convex things have this. That's by Hofer, Wazaki, Zander. This is not true. Okay. It actually is true for slightly more general or slightly more. I'll put a star here since if you ask some hypotheses of star shape that do not imply convexity, then it becomes true. But it's still kind of a. Okay, and then finally. Unknotted minimal orbit. Okay, so this is also a 3-dimensional thing. Okay, so very recent work, I think, published, in fact. So hopefully they're fine with me. They're giving talks about it. So it. This is this was recently solved and shown to be true. So the minimum Reeb orbit of a convex domain is unknotted. Okay, so this is by Abendondolo. And then also is probably no. I'm sure they're going to give a counterexample in there. Maybe example that would be nice, but I think it's so hard to construct a counterexample. Okay. Okay, so somehow, even though convexity has a priori nothing to do with symplectic geometry, like it is not a symplectically invariant thing, it is somehow having an enormous impact on the dynamics, right? It's like having, if you list all of these kind of dynamical properties, somehow magically convexity is doing something. It's doing something in the background that's keeping you from that is not happening for general things, right? Okay, and we really I think the thing I want to emphasize here is that we have kind of no conceptual explanation for this. Like we have no reason to expect. These properties are just things we know. We can prove them using different tools, but we don't really have one conceptual explanation for why that's happening. Okay. Okay. So and the for developing this computational method. So now I'm going to actually talk the topic of the topic. And so there are some conjectures for these properties we'd like to. One thing, and then the other thing is find new conjectures, like new properties of convexity that we didn't know about before. Okay, that we could illuminate this mysterious phenomena that we're seeing. Okay. So our goal now is to probe. We want to probe the behavior. Or maybe Reeb, just Reeb. Okay. And I'm going to go into a lot of detail now. Use polytopes, convex polytopes as sort of our common. polytope is not smooth, but the point is somehow that like the symplectic geometry of the situation actually solves, like, kind of fixes a lot of the problems that you would normally encounter with non-smooth dynamics. Okay. So let me talk about that. Okay, so we're back. We're kind of, I just erased the I needed, so that was kind of unwise. Classic move in a talk. Okay, so let's fix some convex polytope. X inside of R2N. Okay, so I have, again, I'm just going to draw the picture that I just erased. So something very similar. Okay, so this is X. All right. Okay, so on each face, F, there is, instead of a Reeb vector, or instead of a Reeb vector field, there's a Reeb vector. Okay, so RF. Okay, and it's in the tangent space to the face. Okay. So it turns out that when you just have a flat subspace, right? Like, so each of the faces is just a flat subspace. So each of those guys has a Reeb vector field, because it's transverse to the, it is some well-defined Reeb vector field, since the polytope maybe contains 0 is transverse to this outward pointing vector field. And it turns out it's easy calculation to just check that the Reeb vector field is actually just constant. Like, it doesn't depend on it's not a function of the face, it's just a vector. Okay. Okay, so on each face, you have like some constant vector that you can just compute using linear algebra. Okay. And of course, it'll vary. The vector will vary from face to face, but on each face, it'll just be constant. Okay. So it's a nice, like, kind of polygonal vector field. Okay, so now this determines some piecewise constant. I'll be able to say piecewise linear vector boundary of the polytope. Okay. Okay, and so the point now is basically just to study like the characteristics of this piecewise linear vector field, and this is kind of a very computationally tractable problem. Okay, and it's something that we sort of did. I sort of did in joint work with Michael Hutchings, where we basically wrote software to sort of study these things. Okay. Okay. Yeah. So the Reeb vector field. Yeah. What's up? Yeah. So the Reeb. So on each of the faces, you can take like some standard one form that's like a primitive for the symplectic form, and you can restrict it to the face, and then that turns out to be a contact form. You can compute its Reeb vector field, but the thing that happens is that if it's just an affine subspace, then the Reeb vector field is just constant. It's just a vector that doesn't depend on the point. So now it's like, and instead of having a Reeb vector field on the surface of this polytope, I just have a Reeb. Each face gets a Reeb vector, and I could sort of think of it as like a piecewise, like this nice piecewise linear thing, It's just constant. Yeah. I could have said piecewise constant. I don't know. I sort of don't like calling it that, because then the flow is like piecewise linear. Like, it's sort of I don't know. Anyway, so yeah, it's like piecewise. It's piecewise constant, really. Okay. Okay. So what are some key theoretical inputs to this process? So this is sort of, do as much as you want. But there's actually some kind of important theoretical issues that you have to take care of with this that come from the fact that you're dealing with flow with singularity. Okay. So this maybe I'll emphasize that this is all in dimension 4. I think now I could tell you how this is supposed to work in higher dimensions, but at the time we didn't really know how to do that. So now it's all 4-dimensional. So first theorem. Okay. Is that orbits of bounded rotation like works rotation number Okay, so orbits of bounded rotation number are finite polygonal paths. Polygonal. Okay, and in particular, this implies. Okay, so for example, so let me draw you a picture of what the bad situation is and what the good situation is. Okay, bad situation. And I'm going to draw like kind of a three-dimensional here. Okay, so what it's saying, you know, which just these nice finite polygonal paths. Let's go circle around the simplex and in a nice finite way. Okay. On the other hand, you could imagine having some kind of structure like this. So you have a polytope. This is kind of a situation. Okay. And you could imagine instead where the trajectory goes like this. So it kind of circles around, making these like tiny little spirals, spiral, and then kind of comes into the and gets and maybe leaps in some direction along some other face. Okay. But still is sort of doing this like infinite. You kind of these kinds of trajectories completely can appear. In fact, when I originally started writing the program would like routinely get stuck on these kinds of situations. Okay, and a key theoretical input is that actually the orbits that you care about. So the minimum orbits are examples of ones that have bounded rotation in the sense that I talked about. The orbits that you care about actually don't do this. Okay, they cannot do this. Instead, they're all nice and finite. Okay. Well, like the
That, like, going towards a vertex, right?
yeah, it's like spiraling into a vertex in like an infinite way. Maybe a nearby orbit. You could have maybe. I mean, I don't know. It's conceivable that maybe you could have some not too far perturbation of this orbit that would be bad, but badness is sort of something that you can also kind of look for combinatorial, like with the computer. But I mean, the points. I'm not sure. I mean, I can answer your question. Sure. Situation we want to rule out in the sense that we want to know that the minimum we're looking for is not of that type because we will define that with a computer. Is that if of a sequence of convex let's say they converge in, for example, the Hausdorff topology to X. So then in this case, the period of the minimum orbit will converge to the sort of the period of the minimal kind of polygonal orbit, period of the minimum. So this actually is also essentially actually a consequence of this, along with some stuff we know about minimum orbits coming from like floor theory or like kind of sort of more modern symplectic geometry. So this theorem is actually input from the theory of capacity. What's up? That is a great question. That is a great question. Something I am still thinking about to this day is how to get rid of convexity in this whole discussion. It's like there are a lot of situations say very similar things for non-convex objects. Okay, and it gets significantly more subtle. There's actually basic stuff that people use that I'm sort of not mentioning that is like that you kind of use convexity for. So it's a great question. Yeah. Yes. Uh, Yes, 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 yes. In fact, wait, sorry. Let me say something on that. On the next theorem, I'm going to say is sort of in that spirit, okay? Which is that's a good question. Yes. So it converges. In fact, the orbit to an orbit to a minimum orbit there. Okay. And modeling things that we're modeling things well. In fact, non-degenerate. In some particular sense. For so in fact, not the minimum orbit, so the minimum orbit, the minimum orbit period converges to the minimum orbit period. In fact, the minimum orbit converges to some nice polygonal minimal orbit. And not only that, but any non-degenerate polygonal orbit you can go backwards. Like if I wanted to if I look at a little smoothing, then assuming some non-degeneracy property of the polygonal orbit, I can then find a smooth orbit on the smoothing, right? So if I wanted a smooth example of something I'm looking for, I have this tool that will just say, okay, I can actually smooth whatever thing I find, assuming some checkable non-degeneracy property. Okay. Okay, so let me check the time. Do I have like 4 minutes? Okay, so let me now kind of sketch how the program works. 25. Okay, so let me now how the actual program works. Like our intro can help like or like computational methods. Basically, you want to tell me all. I think I'm very dumb, so it's very slow. Okay, so let me get. Okay, so give scope X. Well, what you do is this is what I do. Is you graph gamma, and I'll draw a picture in a second. So first, the vertices are equal to dimensional face of 4-dimensional polytope. Okay. And then there's in the graph EF. If there exists just a line from E to F. Okay, so the picture is I have this or maybe a picture over here. Okay, so for example, here I have E. So everything is 1 dimension down in this picture. So the 1-dimensional faces are the 2-dimensional things in the 40 case. Okay, so I have this like 2D edge, I have this other 2D edge, and if there's like a line, if there's kind of a line connecting the 2 edges inside of some face, okay, then inside of some 3-dimensional face, then I put an edge in the graph for that. Okay. Graph. And this kind of situation will be turned into okay. Then each edge find affine map. From the face E to the face F, and it's just by taking the face E and like flowing it to the F. Okay, and of course, if I take this face E and sort of flow it to F, it's not all of it's going to reach F, right? Some of it's going to go to some other face. So that's why I used the word partially defined. But you can check just being some nice affine map. Okay, if for the points that do reach F. Okay. Okay, so that we now have this kind of graph. Uh, uh, okay, and now computing things like the minimal period. Or something like bounded, like, orbits of bounded rotation number is now just an affine fixed point problem. So what I mean by that is that I can like, now this sort of reduces the problem of finding closed orbits to just finding like cycles inside of this graph and then checking if they have a fixed point and the domain is non-empty. Okay. And then basically the input coming from these theoretical points is that I didn't say this, but there's sort of a bound on the length of the path that we need to check. That's coming from the kind of into this bounded rotation number, right? So we know that minimum orbits have like rotation number 3. So then we have some sort of explicit bound that's like, okay, that means we only need to check like 30 paths of up to like 30. Yeah. I mean, there's some polygonal subset, DE or D, which like the map, and the other like there's some other maps for other. No. For each pair of faces, there's one map. Yeah. Okay. All right. Now, so that's kind of how it works. So basically, I spent about 6 months like implementing this, in Python. It was like really a pain in the butt. The pro this thing, and then I'm going to move on to sort of talk about today. Okay, so the pros of this method. Okay, that is completely rigorous. Or numerical error. Like the way I actually wrote the program at agnostic, so meaning that if you use floats, it'll do in float, but if you use like a lossless number type like fractions, then it will just compute everything in fractions. Okay, and in particular, it'll just give you exact numbers. So that's cool. The answer, I don't have to chat. I don't have to worry about any kind of stability. Okay, and the other nice that's like a generically, I expect the orbits that I find to have smoothings. Okay, so that's coming from the thing I said before. Okay, and cons are really probe new phenomenon in convex dynamics. I need significant improvements in efficiency to do that. Okay. Of course, I'm a programmer, but I'm not like really a person that does this, so it's not a little difficult for me to imagine how to do that. Okay, so let me now talk about some applications that we had, like some stuff that we said in our paper after we kind of developed this method, and then I'll talk about sort of the resolution of a very significant conjecture in symplectic geometry that sort of came out of related methods. Yeah. Okay. So there's some things that we were able to do with this. So first, so let's start with some small. These are just small applications. Okay. So first, the first thing we found, which was pretty cool, was we discovered some new examples of so-called tips. Okay, Zoll here, dynamics. You should read Zoll as like the dynamics resemble the dynamics on the ball. So on the boundary of the ball. And in particular, for reasons that I won't get into, this basically should mean that this thing is symplectomorphic to the ball. Okay, so we found lots of these are really interesting to us because they're sort of like somehow they're like singular, they're weird singular balls that are sort of like that have some interesting interesting stuff going on. Maybe they're not the ball. That would be very interesting too. But basically, finding examples of these is really interesting. So in one example of one polytope is I can literally list its vertices right. Okay, so we have this guy. I think I'm actually missing a vertex, so this is less impressive now that I noticed this. But anyway, there's some explicit list of numbers that I can give you that give you a Zoll polytope. Okay. Okay, and then other things, another interesting kind of corollary of this, the rationality of we have this definition of this minimal orbit, and the fact that it's rational is actually not obvious. So all these methods sort of imply that it's rational. Okay, like this thing will spit out a rational. You have a rational polytope. So if X has, let's just say, rational vertices. And that's also kind of an interesting discovery that came out of this. And I have some other applications, other interesting examples. But I won't go into them since I'm running long. Okay, so the last thing I want to talk about is sort of a big application of related methods. Okay. And then I want to talk about kind of the things that I would do if my computer program was faster. So first of all, all right, so it's not it is the disproof of something called the turbo conjecture. Okay, so let me actually let me tell you a little bit about that. There's this conjecture. Okay, and what it says is that, okay, so we have convex. You can put smooth here, although it doesn't really matter. Okay. Is bounded above by multiplied by the volume. Okay. So, and then I have a 1 over n here. And so this is just a conjecture for the explicit constant that appears in the inequality that I gave you in the table earlier. Okay, so this is basically conjecturing the exact number in that inequality. So this is just a sharp inequality. Okay. So a kind of well-known of this. So someone, an observer been on a stroke, maybe card, but the Mahler conjecture in convex geometry. And the negative k. If you take and this can be more bounded. Okay, so So the Mahler conjecture is a pretty big conjecture, and in convex geometry. So that kind of means the Viterbo conjecture is even harder, of course. But one thing I will say is that the Viterbo conjecture is like a 20-year-old conjecture, which basically was one of the biggest conjectures in geometry. It was like it's probably like the biggest conjecture in a big chunk of symplectic geometry. Okay, and the other thing I want to say is everybody thought this was true. Everybody believed it. Okay. Believe really, really recent. This is like 2004 or 2020. Um, very quickly. Uh, take its product, and then I take its product with the same polygon, but just rotated by 90 degrees. So okay, so basically, so Pazit, who some friend of mine, wrote another computer program using like related but not exactly the same methods. Okay, and she and both of us did tons of experiments. These are all the position x coordinates. These are all the p coordinates. Sorry, I meant to say that. It's a good question. Yeah. Okay, so it's a really good. This is definitely not a counterexample. Okay, uh, so back to the story. So Pazit basically found this understanding of found this example that she was basically programmed a specific question about optimizing the pair-bone inequality over a specific class of polytopes. Okay, and both of us have done an enormous number of experimentation, but basically because my computer program is too slow, could not reach the level of vertices. This is already too many vertices for me. Okay, which sucks. So okay, so then I didn't find this. And in fact, the even more amazing thing is that no matter how far we pushed up, like we tried to do an optimization thing where we just push the systolic ratio up by taking a polytope, varying it a little, pushing the systolic ratio higher, going up, and we always hit exactly this found in this thing. That really made us believe that it was true. But it turns out we just did not have enough computing power. We were looking for existed, just didn't fit. Zed, to the victor goes the spoils. She looked long enough, and eventually she found it. But kind of lucky, but also just because she was really studying this problem a lot. Right? Yes.
One is symplectic work, and the other is in the convex work. So the dimensions, it's only for dimensions.
Well, the volume k cross k. So you should think of the. Yeah, exactly. Yeah. Okay, so now I want to finish. I want to wrap up. Okay, so these computational methods have like more or less already borne fruit. I mean, when Pazit actually that just analytical. You can also completely use their, once you know the polytope is there, computing it for that specific polytope is slow, but not too slow. So you could check exactly in that case. Okay, so now I want to finish with these computer programs if they work. Okay. Failure of a lot of really interesting questions. So one question is what the so basically like Cn is not here should be anymore. We don't have any conjecture for that. The negatives. My money would be on yes, but I clearly don't know what I'm talking about with the video. Who knows? So honestly, who knows? Okay, so this, and I want to emphasize that this would imply. So there's kind of a simple approach to that problem. Okay, and then the last question, which I'll mention, is that another very interesting kind of thing to probe, and this is the thing that I sort of experiment, but was not able to get like enough data on it, is probing relationships between symplectic invariance and the knottiness of orbits. We know that the minimum period is to be unknotted, okay? And a slightly more general conjecture would be that any Conley-Zander index 3 orbit in the of a convex has to be unknotted. And an even more general conjecture would be that there's some function of the Conley-Zander index, this kind of rotation number type quantity, that upper bounds for example, the braid index, or something about the complexity of the closed orbit. And all of the questions that if I made this program faster, I would be able to understand. Yeah, so that's and that's it. So I'll stop there.